In this video, we're going to talk about what are domains and ranges. It's very simple. First of all, let's talk about some basic definitions. Relation. A relation is just a set of ordered pairs. The domain is going to be the input, typically what we know as the X values. The range is the output, what we know of as the Y values. And a function is a relation in which each possible input value leads to exactly one output value. And we say the output is a function of the input. And one of the things that I want you to remember is that in order for a relation to be a function, your x's cannot repeat. Okay, your x's cannot repeat. Your inputs cannot repeat. Let's go ahead and take a look at some examples. It says identify domain range and whether or not the relation is a function. So in the first one right here, I'm going to number it for you. Number 1, we have basically a relation. We have 1, 2, 3, 4, 5 different ordered pairs, each one x comma y, x comma y. Okay, so when we talk about the domain are basically all of the inputs. So in this case, it's going to be all of the x coordinates. So we have 1, 2, 3, 4, and 5. The range are all of the outputs, so all of the y coordinates. So that is going to be 2, 4, 6, 8, 10. In this case, what we are interested in when we're trying to determine whether or not this relation is a function is that we're looking at the inputs. We're looking at the x's. Do any of them repeat? The answer is no. All of my x's are 1, 2, 3, 4, 5. None of them repeat. Therefore, yes, this first example is in fact a function. Notice also that the y's don't repeat, and so that actually makes this a one-to-one function. If we take a look at example number 2, we have 1, 2, 3, 4, 5 different ordered pairs. And once again, the x's are going to be the domain and the range are going to be the y coordinates for each one of these ordered pairs. If we take a look, the domain for this example is odd and even. Okay, because it just keeps repeating odd, even, odd. So I don't have to sit here and write odd, even, odd, even, odd. I can just write odd and even. Then the range are going to be the y values. So here it's going to be the numbers 1, 2, 3, 4, and 5. And notice that clearly we do have x's that repeat. Odd is there 3 times. Even is there 2 times. So the minute you have any of your inputs repeating, then no, this is not a function, okay? As long as any of your inputs, your x's repeat, then you do not have a function. If we take a look at number 3 is more of an example for you to look at, not necessarily something for us to answer, because it's kind of just illustrating for us in what's called a mapping. So notice on the first mapping, we have a relation which is a function. If I were to write these out in ordered pairs, I would write that P goes with M, I would write that Q goes with N, and I would write that R goes with N, okay? So if I had to write these out as ordered pairs, this is exactly what I would do. And the arrows indicate what goes with what. An arrow is very important in a mapping, otherwise you're not going to know what goes with what. So in this case, I can look at all of my x values, P, Q, R, and realize none of them repeat. And because none of them repeat, then yes, this is in fact a function. Let's take a look at the second one. In the second one, notice that none of the x values repeat, and actually none of the output values repeat either. And so yes, this is a function, and more than just being a function, it is what's called a one-to-one function. Okay, it's a one-to-one function because not only do none of the inputs repeat, but none of the outputs repeat either. And it is clear that exactly one arrow is drawn from P to X, one arrow is drawn from Q to Y, one arrow is drawn from R to Z. If we go back to example 8, the first one that we looked at right now with the PQR going with M and N, notice that the N's do repeat. Now, because those n's repeat, it doesn't affect whether or not the relation is a function, but for sure it is not going to be a one-to-one function because those n's do repeat. And then finally, in the last one for part C, notice we have P, X, and then we have Q going with Y and Q going with Z. So if I had to write these out as ordered pairs, I have P, X, I have Q, Y, and I have Q, Z. So notice that because the Q's repeat, then this is not a function at all. Once it is not a function, once a relation is not a function, there's no way it can be a one-to-one function. Take a look at the example here. It says determining if menu price lists are functions. So in this case, it says the coffee shop menu shown below consists of items and their prices. Is price a function of the item? Is price a function of the item? In order for us to answer this, let's take a look back at the notes that we looked at the very beginning of the video. We say the output is a function of the input. The output is a function of the input. So in this example, if we're asking is price a function of the item, that makes price right now the output, and it's going to make the item in this part A going to be the input. So that means that I can look at the items right here, and these are my inputs. And right now, in order for me to determine whether or not this relation represents a function, what I care about is the fact that the inputs cannot repeat. And so I see plain donut, jelly donut, and chocolate donut. None of them repeat. Therefore, yes, price is in fact a function of the item. If we look at part B, and I'm going to erase what I have right now on the screen. In part B, the question says, is the item a function of the price? So in part B, item now is going to be the output, and the price is now going to be the input. So I take a look at the prices because in order for me to determine whether or not a relation is a function, I need to look at the inputs, and none of the inputs can repeat. So right now the price, the way it's worded, the price would go ahead and be the input. I can clearly see there are $2.99, and therefore the $1.99 repeats. This is not a function. What happens in examples like these where they're asking us to find the domain of the function? It does help tremendously for you to be able to understand visually what this looks like. So notice here, this is a parabola. This parabola is going to have a vertical shift down, and it's going up. Therefore, I know the domain is going to be all real numbers, which in interval notation, I can write as from negative infinity to positive infinity. In reality, there's no problem for me to substitute any x value into this function. I can go ahead and substitute positive numbers, negative numbers, 0, and it's not going to give me a problem at all. What happens, however, when I have to find the domain of a function that involves a denominator? Well, here is where you have to look for those problem spots. In a fraction, a denominator can never equal 0. Division by 0 in mathematics is impossible. And because division by 0 is mathematically impossible, what I need to do is determine what value of x is going to make my denominator 0. So I'm going to take my denominator and I'm going to set it equal to 0. So if I grab 2 minus x and set it equal to 0, I'm going to solve. I'm going to subtract 2 from both sides. I get negative x equals negative 2. If I divide by negative 1, I get x is equal to 2. That tells me that when x is equal to 2, I'm going to end up with 0 in my denominator. So my domain are going to be all real numbers, okay, all x values. My x value can be any real number except for x is equal to 2. So sometimes you're going to see this written as my domain is going to be x cannot equal 2. In the case of interval notation, how do I write my answer? Basically, it's every number from negative infinity up until I get to 2, and then union from 2 to positive infinity. So that tells me it's every single number I can substitute for x, but the only one that's not going to make any sense is going to be positive 2, because having a positive 2 for x means I'm going to end up with a 0 in the denominator, and division by 0 is mathematically impossible. When else do I have to worry about restricting my domain? When you have to find an even root. If you remember, you cannot take the square root or the fourth root or any even root of a negative number. Then you're going to have an imaginary answer. Therefore, like in this example, if I want to find the domain of this function, I have to make sure that my radicand, that means whatever is inside of the radical, and I have to set it to be greater than or equal to 0, because it's okay. I can take the square root of 0. I just can't take the square root of any negative number. So I'm going to write 7 minus x is greater than or equal to 0. I subtract 7 from both sides. That means negative x is greater than or equal to negative 7. When I divide by negative 1, by the rules, if you remember, you have to switch the inequality because you are dividing by a negative. So that means that all of my x values have to be numbers that are less than or equal to 7. And if I were to go into the actual radical, into the function, and I try to substitute a number that's less than or equal to 7, like 6. 7 minus 6 is 1. I can take the square root of 1. But if I were to substitute a number that's bigger than 7, like 8, 7 minus 8 is going to give me negative 1, and so I can't take the square root of negative 1. So that tells me that I am most likely correct, and that's a good way for you to check. So this means that my domain are going to be all of the x values such that x is less than or equal to 7. This is called set builder notation. And in interval notation, the way you're going to write this is basically I'm coming from negative infinity until I get to 7, and I do include 7. And if you are having a hard time with interval notation, there are videos that I've done on interval notation. I think that would be really helpful for you to watch. Also, another quick suggestion is to go ahead and graph this, because when you graph it, if you want all the numbers that are less than 7, then interval notation is exactly the way we read, which is left to right. So notice that we're coming from negative infinity until we get to 7. So I feel like it's also very helpful to see it on a graph. So to wrap this video up, domain are all of your inputs, your x values. Range are all of your outputs, your y values. A relation is a function when your x's don't repeat. Also, in order for you to determine domain, remember that we're going to say it's going to be every single real number except for whenever you have a problem spot, which is denominators can never equal 0, and even roots, you got to make sure that whatever is inside has to be positive. Hope you found this video helpful. Remember to subscribe to my channel for more help with math so that you can say, yes, I can do math with confidence. Until next time, thanks for watching.